Hi, welcome to yet another lecture in the NPTEL Haskell course. In this lecture, we will look at a very important concept, which is what exactly does it mean to compute something in Haskell, okay? Or in other words, what is the model of computation in Haskell? In normal imperative programming languages, the main way in which computation happens is that there is a change of state, okay? Namely, there are variables that you use in your programs and you have an assignment statement which will change the value of the variables. So you have to have an idea of a machine with some memory. There are lots of memory locations. Variables refer to some memory locations, and there are instructions in the program that modify the value of the memory locations, okay? So you need to sometimes have all this in mind when you have to understand how a program behaves, because most imperative programs work by changing the value of variables. So you need to have this model in mind, okay, of where does this variable reside, how does its value get changed, when does it change, what gets changed, etc, etc, okay. So you have various issues, like if I pass a variable as parameter to a function, when the function returns, is the value modified or not? There are lots of concerns, okay. In Haskell, of course, all this is implemented in the usual machines that imperative programmers also use, but the computation model that you need to know is at a much more abstract level, and in many senses at a much simpler level, okay. We will see what it is. Yeah, so the main idea, the main mantra here, if you will, is that computation as rewriting, okay. Computation is nothing but rewriting. Okay, use definitions to simplify expressions until no further simplification is possible. This is uh, this is what you mean by computation in Haskell mostly, okay. And this is just a generalization from high school arithmetic, if you will, right? Because if I have 2 plus 3 times 5 plus 6 into 7, then what do? You keep simplifying it till you cannot simplify it any further. 3 times 5 has to be simplified first, so you go to 2 plus 15 plus 6 into 7, and then 15 plus 6 has to be simplified next. 2 plus 21 times 7, and whatever the value of 21 times 7, 2 plus 147, and then that becomes 149. And 149 is in the simplest possible form you can have. There is no operator or anything there that needs to be simplified. At this point you stop, okay. This is exactly what happens in Haskell also. So an answer is an expression like this 149 that we have, that cannot be further simplified. But you have other expressions that could be simplified. 2 plus 5 can be simplified further, okay. There are some built-in simplifications that Haskell gives you. Basic arithmetic, etc, Haskell has to give you. You cannot be expected to implement all that. So 3 plus 5 automatically gets rewritten to 8. True or false automatically gets rewritten to true, okay. These are all built-in simplifications, okay. Good. Now this alone will not suffice, otherwise what is the point of writing programs? So user defined programs also define simplifications, okay. Functions defined by users, defined by us, they really mention, they really tell Haskell what kind of simplifications to perform, okay. Here is an example. Power, which is a function I am defining of type int arrow int arrow int. Power x0 is 1, power xn is x times power xn minus 1, okay. Standard definition, x to the power 0 is 1, x to the power n plus 1 is, or rather x to the power n is x times x power n minus 1, okay. So this is what we are defining for n greater than 0, of course. Now how does it work? So you say power 3 2 in GHCI. What happens? Haskell, the Haskell engine now kicks in. What it does is, it does power 3 2 gets rewritten to 3 star power 3 2 minus 1. Why? Let's look at why this thing happens. Power xn equals x times power x n minus 1 is part of a user definition. Okay. So, this user defined simplification is what happens here. But why does this happen now at this point? Because first of all, the moment you say power 3 2, there are two definitions, right? Power x0 equals 1, power xn equals dot dot dot. Okay. So, the moment you say power 3 2, Haskell will check which of the definitions will apply. So, the first definition will apply only if the second argument is equal to 0, but here the second argument is 2, it is not equal to 0. So, therefore, it applies the user definition and you get power 3 times power 3 2 minus 1. At this point, what should happen? Should the 2 minus 1 become 1, or should you do something like 3 times? Can you do the multiplication at all? Okay, there are various choices. Now, of course, the 2 minus 1 has to be simplified now. Let us see how. So, star requires both operands to be numbers, right? Star is a built-in operator. It requires both operations, both arguments to be numbers and not expressions like power 3, 2 minus 1, etc. So, it has to be simplified first. So, power 3, 2 minus 1 has to be simplified. And power does pattern matching on the second argument. So, the second argument needs to be evaluated to check whether it is 0 or not. So, 2 minus 1 will be simplified again now, and then so that 2 minus 1 will be simplified and it will become 1. At this point, it will check whether 1 is equal to 0 or not, 1 is not equal to 0. So, it should again apply the definition of power, the second line of the definition for power 3 1 as well. But there is this whole line of reasoning for why you go from power 3 2 minus 1 to power 3 1. Okay. So, in Haskell, nothing happens without a reason. Without being forced to happen, let us say. Right, you are forced to simplify 2 minus 1 because you have to check whether the second argument is 0 or not, and that determines what rule you will apply next, and therefore you have to simplify 2 minus 1 to whatever it is to check whether it is 0. So, you have come here now. At this point, you subtract 2 from 1 from 2 and you get power 3 1. At this point, you again have to apply the user definition because you have a star here and star requires both operands to be numbers, and power 3 1 is not a number. So, you have to apply user definition to try to reduce it to a number. So, once you do the user definition, you will get this inner power 3 1 will become 3 times power 3 1 minus 1. Once again, by the same logic, you want to this star here requires both its arguments to be numbers. So, it has to reduce the right hand side argument to a number, but for that it needs to know which rule to apply. So, 1 minus 1 will first be simplified and it becomes 0. At this point, once again, this star requires the right hand argument to be a number. So, you have to again simplify it, and power 3 0 you apply this rule. Okay, the power x0 equals 1 rule. So, power 3 0 becomes 1. So, 3 times 3 times 1. Once again, this outermost star requires the right argument to be an number, but that is not a number, that is an expression. So, you have to simplify this. Okay. So, that becomes 3 and the whole thing becomes 9. Okay. So, you always start at the outermost operator, and if the outermost operator is some built-in operator, then it requires both arguments to be simplified. So, that forces simplifications in the sub-expressions. Okay. So, this is the whole pattern of movement of these reductions or rewriting in Haskell. I am making it sound complicated. Of course, Haskell has some set of rules which it will try to apply, and the set of rules just determine which sub-expression is rewritten. Okay. It is intricate to figure out which sub-expression will be rewritten first. that I agree. But the point is, it is all re-rating, more or less, let's say. Okay, this is the beauty of the of understanding programming in understanding the behavior of programs in Haskell, at least for reasonably simple programs, till you get used to more complex programs. Okay. Okay, so this is it. So this whole strategy is called leftmost outermost reduction. Identify the leftmost sub-expression that qualifies for simplification, such that no expression containing it qualifies for simplification. So outermost. So if I have 3 plus 5 times 2 plus 3 minus 4, then this plus, because 3 plus 5, remember plus is whatever. So this whole thing is 3 plus 5 times whatever. This plus is the outermost operator. So the plus is what? This is what? But you can't simplify it. Simplify it first, right? But simplifying an expression involving a plus means simplifying both arguments. Okay, so this expression will be attempted to be simplified first, let us say. You will attempt to simplify the expression involving the outermost plus, but there are sub expressions which are not numbers, so that forces you to evaluate the sub expressions and simplify them. Okay, so this is the point. Okay, for an expression of the form E1 op E2 operator, where op is a built-in operator, simplify E1 first and then E2 till they are values. Okay, so E1 is an expression, it should become a value like 239 or 49 or 149 or whatever. E2 is an expression, it should become a value like false or true or whatever. Okay, and then you apply the op. Okay, yeah, so okay, so now consider the following simplification sequence, which is not followed by Haskell. Okay, but let's see. Anyway, power 4 minus 2 3 minus 1 is power 2 3 minus 1, power 2 2, 2 times power 2 2 minus 1, right? So you simplify 4 minus 2 as 2, then 3 minus 1 is simplified as 2, so you have power 2 2. But power 2 2 is nothing but 2 times power of 2 2 minus 1, which is nothing but 2 times power of 2 1. Power of 2 1 is nothing but 2 times power of 2 1 minus 1, which is nothing but 2 times power of 2 0, which is nothing but 2 times 1. So overall you have 2 times 2 4. Okay, you might think that this is a nice way of simplifying things. Okay, nice way because 4 minus 2 is simplified first. And after that you are just using 2. After that only 2 is used. After that only its value is used. Okay. Yeah, so 4 minus 2 is evaluated once and 2 is used in the rest of the computation. But what Haskell will do is the following. Following the earlier logic, if I have to do power 4 minus 2 3 minus 1, what Haskell will do first is to determine which rule should be applied, and to determine that it should simplify the 3 minus 1 first. Okay, so it will make this whole expression into power 4 minus 2 2 first. Okay, and then it won't care what that x is, that for applying a user defined rule, you don't need to simplify the arguments to the simplest possible the arguments could be expression. If I have power 4 minus 2 1 or 4 minus 2 2, I will just right. So that is what is happening here. 4 minus 2 times power of 4 minus 2 2 minus 1, which is nothing but at this point the star requires both arguments to be numbers. 4 minus 2 will be simplified to 2, and then you will again do power of 4 minus 2 2 minus 1. Then this will become power of 4 minus 2 1, this 2 minus 1 becomes 1. Then this whole thing becomes 4 minus 2 times power of 4 minus 2 1 minus 1, 1 minus 1 is 0. So ultimately this will, so to do star 4 minus 2 should be simplified to 2, but notice the point here, 4 minus 2 is simplified to 2 here, and then it is again being simplified to 2 here. There are 2 evaluations of 4 minus 2. That is because you are carrying the expression 4 minus 2 around rather than the value around. It appears, okay. This is a problem, right, because you are unnecessarily computing the same expression twice. But Haskell remembers that 4 minus 2 is a replacement for x, okay, because if you recall 4 minus, so your function is power x n x0 equals 1. When I make a call in GHCI or wherever, when I say power of 4 minus 2, 3 minus 1, this 4 minus 2 is x, okay. So 4 minus 2 takes the place of x. So Haskell remembers that 4 minus 2 takes the place of x. So the first time it simplifies the value associated with x, it will use that simplified value everywhere else, okay, when you need to use x. So Haskell remembers that 4 minus 2 is a replacement for x. So the first time once an e occurring in place of x is simplified, everywhere else the simplified expression will be used, okay. So what really happens in Haskell is power 4 minus 2 3 minus 1 is power 4 minus 2 2 is 4 minus 2 power 4 minus 2 2 minus 1, but the left hand side of the star has to be reduced to a number, so it will be reduced to a number 2, but simultaneously, magically almost, the right expression which was power 4 minus 2 2 minus 1 becomes power 2 2 minus 1. See, the two simplification, this is just one simplification. Yeah, Haskell manages this by maintaining some pointers or whatever internally. We don't need to worry about that. All we need to know is that if an expression is being used in place of a variable, when once the expression is simplified, every other occurrence of that e which is used in place of x will be simplified, okay. So that's all we need to know. So then then the rest of the computation proceeds as usual, okay, with just 2 and not 4 minus 2. 4 minus 2 is evaluated only once. But more importantly, only when needed. To be able to determine whether to apply the first rule or the second rule, you don't need to evaluate 4 minus 2. You need to evaluate 4 minus 2 when you have to do the multiplication, okay. 4 minus 2 times something, then that is when you need to evaluate 4 minus 2. At that point it is evaluated, but that value is automatically substituted for by all the other occurrences of 4 minus 2 in that huge expression, okay. So this is what Haskell does. It doesn't matter how Haskell does it, but Haskell does it, and this is one extra bit of simplification that it does. Otherwise, it follows the rule of I will simplify something only when required to do it, and as far as possible I will simplify, I will evaluate everything only once. So the same is the case when one uses a named expression. Suppose I said s is 4 minus 2 of type integer. If I say power s3 minus 1, that is power s2, that is s times power s2 minus 1. At this point I need to know what s is, right, because s is not a number. So s will be now replaced by 4 minus 2, which will be 2. So at this point it becomes 2, but then the right s, this also becomes rewritten to 2 automatically, okay, and you can go on, okay, good. So this is what Haskell does, okay, no repeated computation, compute something only when forced to compute, okay, 2 rules. And what forces GHCI to compute something? Because when you enter an expression in GHCI, internally GHCI tries to print the value of the expression, and that forces that expression to be evaluated, okay. If not for that, then GHCI would never never ever compute anything, because there is no need to compute anything, right? It is computing it because it needs to print something, and for printing it, it needs the value, so it's computing it. Okay, as far as possible. This is the basic underlying Haskell philosophy, but compute means rewrite. Okay, compute means you have an expression, you rewrite it, simplify it, like in mathematics, and not like in other programming languages, go change a variable in memory, etc., etc. Okay. Okay. Now, there is some stuff about order of evaluation. There are two ways of computing 8 plus 3 times 5 minus 3. You can either do 8 plus 3 times 5 minus 3 equals 11 times 5 minus 3 equals 11 times 2 equals 22, or 8 plus 3 times 5 minus 3 is 8 plus 3 times 2. You simplify the 5 minus 3 first, and then you simplify the 8 plus 3, and then you get 22. Of course, the order of evaluation does not matter. Haskell chooses the first option. You have star, and both operands need to be numbers, and it will choose the left argument to simplify the left argument first and then the right argument. Okay. Now, there are two ways of computing power 5 plus 2, 4 minus 4. Look at this. 4 minus 4 is 0, right? So, power 5 plus 2, 4 minus 4 you could either say power 7, 4 minus 4, which is power 7, 0, which is 1, or power 5 plus 2, 4 minus 4, which is power 5 plus 2, 0, which is 1. Here, you are applying the first rule. And for applying this rule, that x need not be a value, right? It could be any expression whatsoever. This is why Haskell chooses the second approach. Haskell will always choose this approach. But the point is, the moment it simplifies 5 plus 2 once, it will be the 5 plus 2 standing for x. If it is simplified once, it will be simplified everywhere else that it is used. Okay, so that is the point. Okay. Now, there is a nice thing that happens because Haskell applies it this way. So, the arguments are evaluated based only on need, and there is something nice that happens because of this, which is that like I mentioned earlier, the second argument needs to be evaluated to test if it is 0 or not, but the first argument need not be evaluated till it is needed to be evaluated. Okay, and this is called lazy evaluation. Lazy means do only when needed, okay, but also smart, because once you do reduce an expression once, you will reuse the reduced value everywhere else that the same expression is being used in. Okay. So, any Haskell expression is of the form some function applied on E. F is the outermost function, E is the expression to which it is applied. Let us say head of 2 colon reverse 1 dot dot 5. Head is the outermost function, 2 colon reverse 1 dot dot 5 is the expression. Now, the definition of head is as follows: head of x colon x is x colon whatever is x. So, your 2 colon reverse of 1 dot dot 5 is already in that form, right? So, it will just return 2 without ever computing reverse of 1 dot dot 5. There is no need to do that. F is head, E is 2 colon reverse 1 dot dot 5. When F is a function name, Haskell reduces Fe using the definition of F. It is also possible that F is an expression that has a function type. Right. So, F could be a complicated expression rather than just a function name. Okay. Okay, that is the point here. Yeah, and so then what will you do? You will first reduce F. You will simplify F to bring it down to a name or some such, and then you will apply F on E. Okay. So the argument is not evaluated if the function definition does not force it to be evaluated. In head of 2 colon reverse 1 dot dot 5, you will just get 2 because the definition of head is head of x colon whatever is just x. Okay. But argument is evaluated if needed. If I have last of 2 colon reverse 1 dot dot 3, 2 colon reverse 1 dot dot 3 is 2 followed by yeah. So let's look at the definition of last. Last of singleton list x is x. Last of x colon x's is last of x's. Okay, that is the definition of last. Okay, so you have 2 colon reverse of something. So then you will try to now compute last of reverse of 1 dot dot 3. Reverse of 1 dot dot 3 is nothing but reverse into empty list of 1 dot dot 3. So you will look at last of reverse into but reverse into empty list 1 dot dot 3 simplifies to reverse into the singleton list 1 2 dot dot 3. That simplifies to reverse into the list 2 comma 1 the singleton list 3, which simplifies to reverse into 3 2 1 the empty list, which is just 3 2 1. Okay. So now you have simplified this whole thing to bring it down to 3 2 1. It's a list form, okay, from an expression form. Now you can apply your now this list is of the form something e followed by e's. Okay, you are waiting for that. The moment you have something like that, then you will just go from last of e followed by e's is nothing but last of e's. Okay, so you have gone here, and yeah, last of 2 1, and then you go to last of singleton list 1, which is 1. Okay, so this forces you to evaluate the argument, the reverse function, but the head, this thing in one step rewrites it to 2 because head of x colon whatever is x. So it does, you don't need to care what that whatever is. Okay. Okay. Now I mentioned that this thing of power 5.2 4 minus 4 going to power 5.20 going to 1 had a nice side effect, which is this, that suppose you have power of 3 div 0 0. Okay, what does it return? Okay, 3 div 0 is officially undefined, right, because you cannot do division by 0. It will throw an exception if you try it in GHCI. But if you follow Haskell strategy, you don't care what the first expression is. The second argument is 0, so you just return 1. That's it. Okay. The first definition here ignores the value of x. So in fact, you could have even written it power of anything 0 equals 1. So it ignores the value of x. So you can also ignore it. So in power 3 div 0, so 3 div 0 is not at all evaluated. Only if you try to evaluate it, you will get division by 0, exception, etc. Now you won't get anything. So you will actually get a value 1 in this case. Okay. So this is an example of what is called a non-strict function. Non-strict being some of the so your output, these are functions, output might be well defined even when some inputs are not well defined. Okay, are not defined. In this case, 3 divided by 0 doesn't make sense. It should throw an exception, but it won't. Haskell allows non-strict functions. Okay, and thanks to its lazy evaluation. Yeah, so just a little more on this. If all simplifications are possible, order of evaluation does not matter. Same answer. This is actually a deep result, which we will not get to. So we'll, for arithmetic expressions it holds, this property holds. For Haskell expressions also this holds. Okay, right. Now there is a difference in that one order may terminate, another order may not, but lazy evaluation expands arguments by need. So lazy evaluation might terminate where other orders will not terminate. Okay. So can terminate, this is important, with an undefined subexpression if that expression is not used. Okay. So, for instance, what would be the result of the following thing? Length of map of div 0, you map div 0 function on 0 dot dot 9. Okay. So, then this should produce 0 div 0, 1 div 0. So, totally, so it is a list all of whose elements are undefined, but it does not matter. To compute length, you do not need the actual values, right, because let us try to look at the definition. What is length? Length of empty list is 0, length of x colon x's is length of x's 1 plus length of x's, right. But the point is that x could be some expression, you do not care what that expression is, some element which is the, yeah, instead of x you could substitute some expression rather than a value, but it is fine. So, now what does map do? Remember, map of div 0, let me just use by 0, of empty list is empty list, is x by 0 followed by map of by 0 x's. Okay, that is the definitions that we have. Let us just try to see how it works for a simpler list, okay, for a shorter list, just so that we can do the example cleanly. So, length of, let us take an example of a list with 3 elements 0, 1, 2, okay. Length of map by 0 of 0, 1, 2, right, equals, to determine, to compute length you need your argument to be of the form something followed by something else. So, you will go internally and that will force you to go and simplify the map, the expression involving map. But expression involving map, if the second argument is of the form x colon x's, it is just the function applied on the first, the head, and then map function on the tail. So, this is nothing but length of right. At this point I am not evaluating 0 by 0, okay, I am just saying f applied on that, I do not need the value, you see, only when I need the value I will evaluate it. But the point is length of this whole thing, that does not need me to evaluate this value, I will just discard it, it is anything whatsoever. So, I will just get 1 plus length of map by 0 of 1 colon 2. Okay, this in turn is 1 plus length of 1 divided by 0 followed by map of, so and so on. The point is, at no point the length function does not even look at the element, right, it just counts 1 towards each element that is in the list. So, it just needs the list to fall in the format E followed by E's, that is all it wants, okay. So, the length function forces map to be evaluated because it wants the overall list to be of the form E followed by something. The moment it gets one element, it will immediately add 1 to its output and then once again do a recursive call on length, which eventually will be evaluated, but at no point will you require to evaluate the elements in the list. So, this length of map div 0 of 0 dot dot 9 should actually give you the value 10, okay, and in case you do not believe it, I can actually go to GHCI, okay, I will show it to you in a bit, okay, right, I am in GHCI, I can start GHCI now. And you can ask for length of map of div 0 and you will cleanly get the value 10. But if you actually try to map div 0 0 dot dot 9, you will get an error because then Haskell will have to display the values of 0 by 0, 1 by 0, etc., and then that will force it to compute it, and it cannot compute it. See, exception division, divide by 0. But you won't get this exception in the length computation case, okay, because you don't need the value, you just need to count 1 towards each value, okay. Okay, let me get back to the slide. Okay, so yeah, this is illustrated here. Length of x's, let x's be map of +1 of 0 dot dot 3. Length of x's is the length of map +1 0 dot dot 3, which is nothing but 0 plus 1. Length of 0 plus 1 colon map +1 of 1 dot dot 3, but the 0 plus 1 is not needed at all. You just add 1 towards its value and then you move on. Okay, so the excess is never fully evaluated. This is the point. Okay. Okay, let's move on. Now, this feature that Haskell does things lazily gives you something enormously powerful, which is that you can actually work with infinite lists, actual infinite lists. Okay, and let us just look at the programs that will allow us to do this. Let me go here, let me go to my temp2.hs or some file that I have. I can define a function of type inf from, infinite from, okay, this is integer arrow list integer. Inf from n equals n followed by inf from n plus 1. That is my function. I am allowed to write functions like this. There is no requirement that my recursion should always terminate. This is a non-terminating recursion. But the point is that, I mean, I am putting an n before that creates a list, but Haskell will cheerfully print it, right? GHCI will print it because all it requires one element, and it will print that element and try to print the next element. For that, it will evaluate inf from 1, and then it will get one element, it will print that element, and then it will try to evaluate inf from 2, etc. Okay. Now, inf list is a list of integer. I can define it to be inf list equals inf from 0. Okay. And if you do this, you will see that if I go to GHCI and if I load temp2.hs, I have a problem. That is because, yes, instead of list of integers, I just put integer. That was my mistake. Let me try to reload. Yes, now it compiles. Okay, so now I can say inf list, and it will try to keep on printing the whole infinite list till it runs out of memory or whatever. But here is the beautiful thing, I can say take 10 of inf list. This program terminates, even though inf list is an infinite list. Remember, Haskell does not try to compute the whole infinite list and then take 10 elements from it. Okay, it will try to expand the definition of take, as we will see in the slides now. Okay. Okay, so inf list is inf from 0, inf from n is n followed by inf from n plus 1. So inf list is actually the infinite list, 0, 1, 2, 3 dot 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 goes on forever. But if I just do head of inf list should be, to apply head, I need the argument to be of the form e followed by e colon e is. So I will try to expand the definition of inf list. Inf list is inf from 0. Inf from 0 is 0 followed by inf from 0 plus 1. That's it. I will stop now, because head doesn't require any computation beyond that. Okay, because head of x colon underscore equals x. So it doesn't care what the underscore is, so it won't compute it. Okay, so you don't need to compute the whole infinite list before you return the value. And similarly, if I want to do take to infinite list, so take to in from 0 is nothing but take 2 of 0 followed by in from 0 plus 1. But at this point, take 2 of, remember, take n of x colon xs is x followed by take n minus 1 of x's. Okay, so that is what it is applying. 0 followed by take 1 of in from 0 plus 1. Once again, it will say, oh, what is in from 0 plus 1? It is 0 plus 1 followed by in from 0 plus 1 plus 1. Okay, it doesn't even care to simplify 0 plus 1 to 1 at this point of time. All it requires is take requires you to pick out some elements. So the elements could be just expressions, need not be values. They will finally be evaluated to values when you display them in GHCI or whatever, when you use them. Okay, so this is take 1 of 0 plus 1 followed by in from 0 plus 1 plus 1, but that is nothing but 0 followed by 0 plus 1 followed by take 0 of whatever. So take 0 has a definition which says take 0 of whatever is just empty list. Okay, so at this point that will be just empty list, and so your overall thing is 0 followed by 1 followed by empty list. Okay, which is nothing but 0, this is 0 1. So this is a beautiful thing that you can do with Haskell. You have expressions where the sub expressions are actually infinite lists, they won't terminate, but you can actually use them in some larger computation where it terminates. Okay, and all this happens because of laziness of Haskell. And now the range notation which we talked about earlier can actually be extended to infinite lists. Rather than just have m plus 1 dot 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 till n, I can have m dot dot, which means m plus 1, m plus 2 and so on forever. Or I could also have m comma m plus d dot dot, which means m plus d, m plus 2d, m plus 3d and so on. Okay, and using infinite lists sometimes often simplifies programs. For instance, here is a program, index of x in L. I want to find the index in the list where x occurs first. Okay, now the list will be finite, let us say, but the point is, what I will do is I will rather than do some count or whatever, what I will do is I will do this zip of 0 dot dot the infinite list. So I will line up the infinite list 0, 1, 2, 3 goes on with my list L. But the beauty of zip is that it will cut off this thing, right? So you will actually get a 0 comma x1, 1 comma x2 dot 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 n minus 1 comma xn. I should have started the indices from 0, but it's okay. Right? So you don't need to specify length or whatever. I just say zip 0 dot dot, zip will automatically cut it off beyond that length, because recall the definition of zip, zip of empty list, whatever is empty list, zip of whatever empty list is empty list. Right? If I have x followed by x's and y followed by y's, then you pair up x and y and then you zip x's with y's. So the point is, this x followed by x's, that x's could be an infinite list, but I don't care. Okay, especially in this case, if one of the things is empty list, then the overall value will be empty list. Okay, fine. So I do this. What I am doing is I am pairing up indices against the values by using this zip, and if I do this go, if that go ever reaches the empty list, then I return -1, but otherwise if the y part of the first element is a pair I comma y, if x is equal to y, then I return I, else I do go x piece. Okay, so this is the kind of programming I can do with infinite lists. Okay, so all this leads us to do this beautiful program in Haskell for generating the list of all primes. Okay, the list of all primes actually. Okay, so this is the method of the sieve of Eratosthenes. Okay, what do you do? Start with the infinite list 2, 3, 4, etc. The first element is a prime. Remove all multiples of 2 from the tail and recursively compute primes. Now the point is, remove, when I say this, it is impossible to first remove multiples of 2 from 3 dot dot and then repeat this procedure. Right, because that is an infinite procedure, right? Remove multiples of 2 from 3 dot dot means remove all multiples of, that is an infinite task. You can't do all that and then do this thing. But the point is, Haskell will interleave this kind of computation. So let us look at the Haskell program. You do sieve of 2 dot dot, which is the infinite list 2, 3, 4, etc. Where sieve of p colon excess p is a prime is where is p colon p followed by sieve of. You apply the sieve on a smaller list. What is the smaller list? All x from x's such that x is not a multiple of p. Right. So you pick out the head as the prime and eliminate all multiples, and then you once again recursively do this. I mean, in human language we say and once again, but Haskell interleaves all this. Okay. So the nth prime is primes bang bang n minus 1. Okay, that's what you want. The first 100 primes are take 100 primes. Okay, that's it. Primes is one infinite list of all primes. Okay. Actually, if you want to follow how this is computed, I have left a slide here. I will put it up on the in the material that we upload along with the videos. You can follow it and try to understand what is happening, but this is just an extension of the principle that I have mentioned earlier. Okay, I'll stop with this, but before I go, I'll actually program the primes this thing, and I'll take the first 1000 primes, let us say. Okay, just for you to see in action how this happens. Primes is an infinite list of integers. Primes is defined to be sieve of 2 dot dot, where sieve of prime p followed by x's is nothing but p. You extract p and then you apply sieve on the sublist x such that x comes from x's and x mod p is not equal to 0. That's it. Okay. Let's save this. Let's load this in GHCI. It compiles. If I say primes, of course, it will keep on running till I press Ctrl C and interrupt it. But I can actually do meaningful things like take 100 primes. That shows you the first 100 primes. Right? I could even do take 1000 primes, take 500 primes, whatever. Right? Those are the first 200 primes. Okay? It's so simple. Okay? Imagine how hard it is to write a number to check if something is prime or to generate some primes, but here you have a program that is so beautiful, and it uses the full power of laziness that Haskell offers you. Okay. So thank you. I will stop this lecture now. In the next lecture, we will look at further concepts. Thank you.